let v be the vector 1, 2, 3 in 3 dimensions in R3, and let w be the vector 2, 5, 10, and we want to find the projection of the vector w onto the vector v. So if we have some vector w here and some other vector v, then the projection, also called the orthogonal projection, would be this vector in blue. So it's a multiple of the vector v. You're taking the portion of w that is in the direction of v. Or sometimes in the opposite direction, if the vector w was pointed this way and v is over here, then you're really projecting onto this line. You're going straight down orthogonally, and the projection vector would be this one. Now the formula for the projection of the vector w onto the vector v, it is a multiple of the vector v. So it's some constant, some scalar. It's a scalar multiple of v. And that scalar is the dot product v dot w divided by the dot product of v with itself. So that's the value of the scalar. So this is just some number times v. So the projection, this was v here, so the projection is just some multiple of v. In this case, it looks like it's about half of v. And in this case, it looks like it's negative, and then maybe it's a third of v. So you're going to have some fraction, or in general, of the vector that you're projecting onto. Okay, before we do this particular example, let's just investigate some very simple projections. V dot v is the magnitude of the vector v squared. So it's interesting if the vector v is a unit vector, and in 3 dimensions, the nice unit vectors are I, j, and k. So let's just take a look at the projection of this vector w onto the vector I. So I dot I is 1, 0, 0. So I dotted with itself is going to be 1 times 1 plus 0 times 0 plus 0 times 0, which is 1. So this denominator is going to be 0, and we're just going to get w dot I times I. So we're going to get a multiple of I. And since w is the vector 2, 5, 10, we should get exactly the I component of w when we project onto I. And we will notice that w dot I, so I is 1, 0, 0. And when you take the dot product of I with w, you get 2. So this is 2I, and that is 2, 0, 0. If you project w onto j, then we should get 5 times j. So this should be 0, 5, 0. And if we project w onto k, then we should get 10 times k. So we should get 0, 0, 10. And let's just verify one of these. The projection of w onto j is w dot j. It doesn't matter what order you do this dot product in. I seem to be doing it in the reverse order of the formula that I wrote here. Over j dot j, which is 1, times j. And w dot j, w is 2, 5, 10, and j is 0, 1, 0. When you do the dot product, you get 0, 5, 0. Add those together, you get 5j, which is, as we said, 0, 5, 0. Okay, so now that we have an understanding of projection, let's calculate this kind of random projection. In order to do that, we need to know v dot w and we need to know v dot v. So let's go with v dot w is equal to 1, 2, 3 dotted with 2, 5, 10. And this is 1 times 2 is 2, 2 times 5 is 10, and 3 times 10 is 30. So those are the products of the corresponding components, and then we have to do the sum of those products, and that's 42. And v dot v is 1, 2, 3 dotted with itself, and that's going to give us 1 times 1, 2 times 2, 3 times 3, and add those together, and we get 14. So now the projection, let me do this in red so that it doesn't. The projection of W onto V is going to be the fraction with 42 on the top, 14 on the bottom. It's 42 over 14 times the vector V. Again, the projection onto V is a multiple of V. Our multiple is 3. It's 3V. 42 over 14 happens to be 3. So 3V is, multiply this by 3. So 3 times the vector 1, 2, 3 is the vector 3, 6, 9. So there it is. The projection of W onto V is 3 times V in this case, the vector 3, 6, 9.